Hello and welcome to today's video. I'm Heidi Bankoff. Today we're going to learn about earthquakes, what causes them and where they occur, and what factors affect the severity of damage they cause. This picture is from Japan 2011, one of the most deadly and costly natural disasters in history. Earthquakes can cause immense damage. An earthquake is defined as the sudden motion of Earth caused by the release of energy that's stored in rocks. This picture is from the earthquake that rocked Haiti in 2010. And here's a picture of Italy in 2016. Fortunately, most of the earthquakes that occur are small and less damaging. This is an extremely important topic because earthquakes happen all the time in parts of the world. This map shows the earthquakes that have happened in just the last 7 days. The orange ones occurred today, the red ones in the last hour. You can see that there were plenty of pretty powerful earthquakes in just the last few days. So let's talk about why earthquakes happen. First, our Earth's surface is broken up into different pieces called tectonic plates. These plates tend to move independently, but very, very slowly. As those plates move, they grind past each other, deforming the surface, causing earthquakes. They slide around on top of a part of the mantle called the asthenosphere. That movement is driven by churning in the mantle. More on the layers of Earth, their qualities, and how they behave another day, though. Earthquakes don't happen randomly throughout the surface of Earth. They happen mostly along the boundaries between these tectonic plates. The location of earthquakes is one of the major pieces of evidence for the theory of plate tectonics. Here you can see the plate boundaries. And here you can see the occurrence of earthquakes in the last 30 days. There is definitely a pattern to where earthquakes occur. Why do earthquakes occur in those places? The mechanisms that cause earthquakes were first proposed by H.F. Reed after the 1906 San Francisco earthquake. His theory was called the elastic rebound theory. Here's how it goes. Stress is a force exerted on an object. Tectonic forces, that mantle churning, puts stress on the rocks. If a rock is stressed by a tectonic force, it undergoes elastic deformation. In other words, it bends. Similar to a rubber band, as the rubber band is stretched, it builds up stress and becomes deformed. When the stress is released, the rubber band springs back and releases that stored energy. Tectonic plates move at a rate of about 1 to 6 centimeters per year. Friction, however, prevents the rocks from sliding past each other continuously. As a result, the rock stretches or compresses elastically. When the buildup of energy overcomes friction, that rock slips along the fault line, generating an earthquake. The rock may move a few centimeters to a few meters, depending on how much energy has been stored. This causes stress in other areas too, resulting in aftershocks. There is a fault line in this GIF, and you can clearly see how the road shifts from its original pathway along this line. Here's another picture that shows the same thing. As plate A subducts or moves under plate B, it pulls plate B along with it, putting strain on this one. Eventually, that strain overcomes the friction and plate B snaps back to its original shape. Fractures in the Earth's surface where rocks are being scraped against one another are called faults. Here you can see a picture of the San Andreas Fault in California. The plate on the west side of this fault is being pushed north, while the eastern side is being pushed south. Here's another satellite image of a fault in China. You can see how the rocks have slowly slid past each other over the years, dividing this mountain range in half. Here's the fault line right around here. As we mentioned, earthquakes happen along fault lines. Movement may occur at the surface, or it may occur deep underground. The exact place where movement starts is called the focus. It's usually below the surface. If it's deep below the surface, it can cause damage to a larger area than a shallow earthquake. The epicenter is the location of the Earth's surface directly above the focus. You often hear about what city is at the epicenter of the earthquake instead of the location of the focus. This map shows the location and depth of earthquakes in the last 30 years. You can see how they're not evenly dispersed throughout the world. The vast majority of earthquakes occur along plate boundaries. So what tools do we use to detect earthquakes? This is a seismograph, and the record that it produces is called a seismogram. You have a heavy tool that stays in one place while the ground shakes beneath it. This is a seismogram. It's a record of the waves from an earthquake. And as time goes on, you can see that needle scraped along the paper, producing waves just like the way the ground shook. There are a few types of waves that a seismograph records: S waves and P waves and surface waves. These slinkies are a good analogy for the way the ground moves during an earthquake. P waves compress and stretch the ground as they go by. S waves move the ground side to side as the wave passes. I think it's easy to remember this kind because it looks like an S. These waves have different characteristics, and they've given us different information about what's going on deep inside the earth. P waves move like this. They are the fastest waves, so on a seismogram, they're the first indication that an earthquake's happening, hence the name primary. They are sometimes called push-pull waves because of how they make the ground move, and they can travel through anything: solids, liquids, gases. Here are your P waves. They're the first ones to arrive, primary waves. S waves, or secondary waves, are slower than P waves, so they show up on the seismogram later. They can only go through solids, and they go side to side. There's a lot of S words related to these waves. Here are your S waves, or secondary waves, on this seismogram. And lastly, surface waves. These are the slowest and most destructive waves. They usually have the greatest amplitude or height of waves, but fortunately, they tend to travel the shortest distance from the epicenter. They diminish in an earthquake as they ripple out from the epicenter. The study of seismic waves, or earthquake waves, has led to some important conclusions about the structure of the earth. The deepest humans have ever dug into the ground is only about a third of the way through the crust, in part because the temperature inside the earth increases as you go down, and it gets too hot to drill much further. Therefore, we have to rely on other data to tell us what's going on below the crust. We've used seismic waves, kind of like X-rays, to look deep inside the earth. When earthquakes occur on this side of the earth, the waves can be detected by sensitive equipment all over the world. But not all the waves. Remember that S waves only go through solids? The liquid outer core of the earth leaves a shadow on the other side of the earth where some waves don't reach. P waves also bend or refract as they travel through areas of different density. If an earthquake occurs here, you will not detect waves here or here. This is called the shadow zone. The S waves were blocked by the liquid outer core, and the P waves were bent or refracted as they moved through different regions of Earth. Put the data from thousands of earthquakes together with some pretty sophisticated math, and you get a clear picture of how the Earth is structured. Let's talk about the scale that we use when we are describing the strength of earthquakes. The magnitude, or moment scale, measures the amount of ground shaking during an earthquake. The amount of energy that an earthquake releases depends on the amount of stress that's built up along the fault line and the qualities of the rock at that location. This is a logarithmic scale. Each number is 33 times more powerful than the previous.
When an earthquake hits, we're all pretty used to hearing about its magnitude. A 5.8 for the Virginia 2011 quake, a 7.0 for Haiti's devastating quake in 2010. But what exactly do those numbers mean? They represent the energy an earthquake releases, basically how powerful it is, and the numbers build exponentially. And that can be a hard thing to picture. That's why this animation is so handy. It shows just how big the difference is from one magnitude to the next. Each magnitude is basically 33 times more powerful than the last. That means a magnitude 7 earthquake is 33 times more powerful than a 6. So take a look at that 5.8 Virginia quake. It looked pretty small compared to those 6.9 quakes. But compared to that 7.7 Sumatra quake, it looks tiny. And it's all because of this exponential scale. It builds fast, by a factor of about 33 with every jump. So the difference between two magnitudes, between a magnitude 6 quake and a magnitude 8, is 33 times 33, or 1,089. Do the math, and a magnitude 9 earthquake, like Japan's catastrophic Tohoku quake in March 2011, is 35,937 times more powerful than a magnitude 6. Even though we've gotten really good at measuring earthquakes, it's still impossible to predict them. Scientists can't say when the next colossal earthquake will happen, but they do know that one will, and that it's important to be prepared when it does. For Our Amazing Planet, I'm Andrea Mustaine.
Fortunately, the most intense earthquakes are very rare. A magnitude of 1 or 2 are detectable by sensitive seismographs, but rarely felt by humans. A magnitude of 5 or 6 can cause damage, depending on the number of factors that we'll discuss in a second. A magnitude of 8 or greater is considered catastrophic, with lots of damage and loss of life. There are lots of magnitude 2 earthquakes, estimated at 1 to 2 million each year. There are only, on average, about 3 magnitude 8 earthquakes each year, and sometimes 1 magnitude 9 earthquake. Magnitude 10 theoretically exists, but we've never measured one that strong. Magnitude measures the amount of energy released by an earthquake, but there's more to measuring earthquakes than just the numbers. For example, it's important to note how an earthquake affects the people of the region. Let's compare 2 earthquakes. The Great Alaska Quake of 1964 was powerful. It was a magnitude 9.2 earthquake, one of the largest ever recorded. 131 people died, and it caused $750 million in damage. But compare that to the Indian Ocean earthquake of 2004. It was a magnitude 9 earthquake, but it killed almost 300,000 people and caused hundreds of times more in economic damages than the Alaska quake. Whole towns were wiped off the map, and the country of Indonesia was simply devastated. So why did these quakes have such different outcomes? Again, magnitude measures the amount of energy released by an earthquake. The earthquake intensity measures how strongly the quake impacted a specific location and the people in it. There are lots of factors that affect how much damage an earthquake can cause. The magnitude of the quake makes a difference. The more energy in an earthquake, the more destructive it can be. The distance from the epicenter also makes a difference. The epicenter is the point at the surface right above where the earthquake originated, and it's usually the place where the earthquake's intensity will be the greatest. The geology of the area also affects its intensity. The nature of the ground at the surface of an earthquake can have a profound influence on the level of damage. Loose, sandy, or soggy soil can liquefy if the shaking is strong enough and long enough, for example. That doesn't bode well for any structures sitting on the top or on the surface. These buildings, as you can see, sunk into the sandy soil when the earthquake hit. Population matters. Are there a lot of people living near the epicenter? Fortunately, in Alaska, the epicenter was in the middle of nowhere. Anchorage was the closest city, but it was not heavily populated at the time. Architecture. Even the strongest buildings may not survive a bad earthquake, but architecture plays a huge role in what and who survives the quake. In 2010 in Haiti, for example, it was made far worse by poor construction, weak cement, and unenforced building codes. And then there are secondary effects. Secondary effects sometimes cause the most damage. A tsunami is a wave of water caused by an earthquake. This is a graphic or a model of the wave that was caused by this earthquake off the coast of Sumatra in 2004. It's the reason that the quake was so deadly. It killed people in 14 countries, primarily Indonesia. Landslides after an earthquake can wipe out huge swaths of buildings. Fires after the San Francisco earthquake of 1906 destroyed much of the city. Gas lines leaked and fueled fires that all but destroyed the city. And then there are social impacts. Economic losses, disease, and displacement of people, like you see in this picture, fleeing Haiti after their giant earthquake in 2010. The earthquake in Haiti in 2010 was so deadly, partly because of poorly designed buildings, but also because of the resulting outbreak of cholera that killed tens of thousands of people in the days after the quake. Seismologists don't really have the ability to predict earthquakes, but we can determine where the risk of experiencing one is the greatest. Seismologists use sensitive ground tracking equipment to determine how much stress has been built up in the crust along the fault line. If we know the likelihood of an intense earthquake occurring in a certain region, we can take the proper precautions to save lives, like ensuring that buildings are designed to meet the risk and having an emergency fund to help the people impacted by the event. Hopefully, you never experience a severe earthquake, but if you do, remember to drop, cover, and hold. Standing in a doorway is not always the safest place to be in the building. Drop to the ground, cover your head and your neck, and hold on to something so that you don't move around within the room. Stay safe, and thanks for watching.